Hello, everyone. Welcome to this talk. My name is Ahmad, and today I will be presenting to you our work on a program logic to verify signal temporal logic specifications of hybrid systems. There's a lot going on in this title, so let me unpack it for you a bit. Throughout this talk, I'm going to be talking about verifying properties about hybrid systems. So let me first explain what exactly a hybrid system is. Loosely speaking, a hybrid system is a system that exhibits both discrete and continuous behaviors. Examples of hybrid systems around us range from, say, autopilot systems in self-driving cars and airplanes to satellites in orbit. With the recent technological advances, hybrid systems are becoming increasingly commonplace around us. With the increase then in this presence of hybrid systems around us, there is naturally an increase in the need to verify such systems, especially if lives depend on their correct functionality. For example, a car autopilot system, you would want to verify and make sure it does not have incorrect functionality if you're going to really trust the system. There have been works aimed at reasoning about hybrid systems. A particularly well-known logic is differential dynamic logic, which proves properties about the end states of the execution of a hybrid system. Note here that there are zero guarantees about any intermediate states of the system or on any infinite executions of the system. Examples of properties that we can reason about with DL include this box alpha. All traces of hybrid program alpha satisfy this property phi upon termination. And then we also have diamond alpha phi, which says there exists a trace of hybrid program alpha that satisfies property phi upon termination. Now that I've briefly introduced DL, let me introduce you then to think about how would you go about proving some property. A self-driving car never collides with a foreign object with the kind of reasoning that is enabled by DL. Spoiler alert, you cannot use DL for this property because it is not sufficient to say that the car is not colliding with an object when the program terminates, since there may have been a collision during the execution of the autopilot program. We need here to reason about intermediate states of the hybrid program, and this is exactly where differential temporal dynamic logic comes into play. Properties of interest include box alpha, box phi, which says all traces of hybrid program alpha satisfy this property phi globally, that is at all times. Note here then that there are guarantees on all intermediate states, for this example, all intermediate states of the execution, as well as any infinite executions of the system. Moving on to a slightly more involved property, consider this. The same self-driving car that we've been talking about, this self-driving car eventually starts moving. This could be phrased as something along the lines of there exists a time t, such that at all times after time t, the car's speed is non-zero. This property, speed is non-zero, can be encapsulated in this example using this predicate phi, and our example then becomes box alpha diamond box phi, which as a reminder then says for all traces of hybrid program alpha, there exists some time after which property phi is always satisfied. Notice here the use of this alternating temporal modalities, that is, we have this diamond followed by a box, a feature that is not supported by DTL. This is where DTL2 comes into play. DTL2 conservatively extends DL, and then it allows for properties of this class to be expressed cleanly. So far I've been unpacking the program logic part of the title of this paper with some background information. Let us now shift gears then to the signal temporal logic, or STL, bit from the title. STL is a logic well known in the controls community. It is primarily used to reason about temporal properties over continuous signals. Note that while the program logics that I've mentioned so far can prove properties about all traces of a program, STL only focuses its efforts on one such trace. But STL can not only prove properties about intermediate states of a signal, it can do so in given time intervals. For example, we can say something like box AB phi, which means this property phi is true at all times between A and B seconds from now. We also have this diamond AB phi, which says that there exists a time between A and B seconds from now, at which point property phi is true. There's also this notion of verifying in the title of this talk. For our purposes, as just as a clarification, verification essentially focuses on safety and liveness. Safety essentially means that nothing bad ever happens in the system, and this usually corresponds to the box temporal operator, whereas liveness refers to something good eventually happens, and this typically corresponds to the diamond temporal operator. Note that if you've come across this kind of notation before, the box is the same as G for globally, whereas the diamond is the same as F for finally, in that something will finally or eventually happen in the future. Now that I've unpacked the title a bit and introduced some related works briefly, let me go over why DTL2 or STL by itself is not good enough. Consider the property, this car that we've been talking about, it applies its brakes within 2 seconds of spotting some obstruction in its path. This property could look something like obstruction equals true, implies for all traces of autopilot, this hybrid program autopilot, it is the case that within 0 and 2 seconds from now, brakes are true. That is, the brakes have been applied. Note here the use of within 2 seconds, a property that STL would really thrive at. But we need to be able to reason about all traces of the car's self-driving program. So there needs to be some notion of quantification over program traces. Neither DL or any of DL's children logics, which includes DTL2, is sufficient to express this crucial property of interest. We need aspects of both logics to reason about properties of this class. Well, let me present to you our fusion of DL and STL. We call it signal temporal dynamic logic, or STDL for short. STDL inherits from DL, meaning it can quantify over program traces, and then STDL uses a fragment of STL, which means it can express safety and liveness properties over specified time intervals. Examples of properties of interest include box alpha, box AB phi, which says that for all traces of this hybrid program alpha, property phi is always true between A and B seconds from now. We also have box alpha diamond AB phi, which says for all traces of program alpha, there exists a time between A and B seconds from now, at which point phi is true. And these properties may sound a little abstract for now, but I will state them again at a later slide and then go over in detail exactly what they entail. So please do not worry too much if you do not understand them fully just yet. So far I've introduced to you some background knowledge necessary to understanding this talk and then motivated our program logic STDL. For the remainder of this talk, I will focus on STDL, the program logic itself, including syntax, semantics, and the STDL proof calculus, and then I will later part with some concluding thoughts. First up, hybrid programs in STDL. Since STDL is aimed at verifying properties about hybrid systems, it stands to reason we need some way to express hybrid programs that represent such systems. As in DL, the hybrid programs in STDL are non-deterministic programs, alpha and beta, that model hybrid systems. These programs can be discrete variable assignments, X is assigned this value theta. They can be tests, question mark chi, and this is similar to say if statements, if you're more familiar with that kind of notation. We have differential equations, x prime equals theta, ampersand chi, which says x prime evolves according to some condition, and then ampersand chi is essentially a exiting condition for the differential equation. We can have non-deterministic choice, alpha union beta, where you pick either alpha or beta. We can have a sequential composition, alpha semicolon beta, where we run alpha first, following which we then run beta. And then finally, we can have non-deterministic finite repetition, alpha star. There is also a notion of states and traces in STDL. Informally, a state is a valuation of the program variables at a certain point in time, whereas a trace is the evolution of the variables over time. In the figure on the slide here, we have some variable x, this is along the y-axis, and then we also have our time axis, and then these lines, these continuous lines are essentially the trace of the program over time, and then looking at one particular value of time, whatever value the variable x is going to take, that will correspond to the state of the program. Representing properties about states and traces, then, we have state and trace formulas in STDL. A state formula phi or psi can be the comparison between two terms in the logic, theta 1 and theta 2, or it can be the negation of another state formula phi, or the disjunction or conjunction of formulas phi and psi. It can be a universally quantified state formula over some variable x. For all x, this phi is true. Or it can be an existentially quantified state formula. There exists an x such that phi is true. And then finally, a state formula can be a program necessity, box alpha pi, indicating all traces of alpha starting in the current state satisfy this state formula pi, or it can be its dual, this program possibility, diamond alpha pi, which says there exists a trace of alpha starting in the current state that satisfies this trace formula pi. A trace formula pi then can be the negation of another trace formula pi, or it can be a state formula phi, which essentially just means that phi evaluates to true at the end of the trace, or it can be a temporal necessity, this box AB phi, saying that at all times between A and B seconds from now, this phi is true, or it can be its dual, this diamond AB phi, which says there exists a time between A and B seconds from now. Let us now take a closer look at the kinds of temporal properties that we can express over traces of hybrid programs using our program logic STDL. First up, we have, as promised before, box alpha, box AB phi, which as a reminder says that for all traces of the hybrid program alpha, at all times between A and B seconds from now, this property phi evaluates to true. If we look at the figure on the slide, note that all traces of alpha, in this case, it's only two traces. So both traces of alpha satisfy phi at all times between A times A and B of their execution. We can also express box alpha diamond AB phi, which says for all traces of program alpha, there exists a time between A and B seconds from now, at which point property phi is true. If we look at the corresponding figure on the upper right, we notice that for each trace of alpha, there exists some point between times A and B, at which point this property phi is true. Moving on to the program possibilities then, the first property we can express is diamond alpha, box AB phi, which says there exists a trace of program alpha such that at all times between A and B seconds from now, the property phi is true. The corresponding figure on the bottom left quadrant on this slide indicates one trace of alpha. In this case, it is the green trace, in which at all times between A and B, this property phi is globally satisfied. And then finally, we can have this diamond alpha, diamond AB phi, which says there exists a trace, of program alpha, such that there exists a time between A and B seconds from now when property phi is true. The bottom right quadrant then shows the execution of alpha with two traces, one of which, and in this case, it is the blue trace, satisfies property phi at some point between times A and B. So these are the four main temporal properties of interest that we kept in mind as we developed our logic. So now that I've defined briefly the syntax and semantics of STDL, let us now shift gears to the proof calculus of STDL. We use a technical trick involving normalized trace formulas to produce a clean calculus for STDL. There are essentially two forms of normalized formulas. I will go over one of those, and the other is similar. I will just skip it in the interest of time. For the first form of normalized formulas, given some trace sigma and state formulas phi and psi, we say that sigma satisfies phi box and box AB psi if and only if. And here this box and essentially is a special conjunction of a state and a trace formula. So sigma satisfies phi box and AB psi if and only if the last state of sigma satisfies phi, and then sigma satisfies box AB psi as a whole if sigma is a trace that terminates, or sigma satisfies box AB psi if sigma is a non-terminating trace. In the examples on the slide, if we focus on the left, we have a trace of sigma that satisfies psi throughout times A and B, and then it terminates in finite time. And when it does, it satisfies phi. So that is the first part of this satisfaction. And then on the right, we have if sigma does not terminate, which is indicated by these ellipses at the end of the trace, the formula is satisfied when psi is true between times A and B, and then there is no requirement on phi, again, because sigma does not terminate. So last state of sigma does not really exist. And then the normalized formula phi box or diamond AB psi is defined similarly. Here, this box or is a special kind of disjunction between state formula phi and the trace formula diamond AB psi. And as I hinted before, it's similar, so I will not go over it in the interest of time. Moving on to the actual calculus of the logic then, since we take special care to make STDL a conservative extension of DL, our logic inherits its non-temporal rules from DL. We then present sound temporal rules to break down any STL temporal formula into equivalent non-temporal formulas, which are then proven using the proof rules from DL. All of this may sound abstract at this point, so let us actually take a look at a couple of concrete examples of proof rules from STDL. First up, assignment. Two things I want to note here before one of which is the assignments in STDL and in DL indeed occur, they're discrete steps, they occur in zero time. It is a like shifting of states from one state to another along the same value of time. And then the second thing I want to point out here is that there are no satisfaction requirements in STDL formulas for time intervals after a trace has already terminated. And I will explain exactly what that means in a bit. But one of the rules for the assignment are shown on this slide. Focusing on the conclusion of the rule first, we have for all traces of hybrid program, X is assigned a value of theta. The formula, this normalized formula phi box and box AB psi is true. And again, as a reminder, this box end is essentially a special form of conjunction between a state and a trace formula. Now, let us focus on the premise of the rule then, which logically leads to the conclusion. The premise has two parts. Either A and B are both zero, in which case we need psi to be true initially, following which we assign this value theta to X, after which we need both phi and psi to be true. And this is shown in the figure on the left. For the second part, if A is greater than 0 and then B is greater than or equal to A, we assign theta to X, following which phi needs to be true. And this is shown in the figure on the right. Note here that the assignment happens at zero time, at time 0, as I hinted before, following which the trace terminates. The formula for the conclusion, it required psi to be true between times A and B, but since the trace does not even reach time A, there are no satisfaction requirements on psi for this second case. So that was assignment. Let's now move on to a more complicated proof rule, the sequential composition of two traces. One of the rules for sequential composition of hybrid programs alpha and beta is shown on the slide. Recall this is represented using this semicolon operator. One quick note on the notation that is used on the slide, this timed alpha q is equivalent to executing this program alpha and then timing how long it takes for alpha to terminate, following which this time taken for alpha to terminate is output as a fresh variable q. This notion of timing hybrid programs is introduced and explained in detail in the paper, but here I want to note that this sort of timing is essential to having sequential composition work with STL temporal specifications in our logic, as I will indicate in a bit. So looking at the conclusion of the rule then, it says for all traces of alpha semicolon beta, this normalized formula phi box and box AB psi is true. Now, there are essentially three cases that we need to consider for this kind of a sequential composition. These cases are encapsulated using this min and max notation in the premise of the rule above, but let me break it down for you. Case 1, A is less than equal to Q, which is less than equal to B. That is, alpha is a program that terminates at some point between A and B. This is shown in the figure on the slide. Note that the formula needs this property to be true for all traces of alpha and beta, but I am only going to show one such trace of each program to make the figures slightly easier to follow. So we're considering alpha sequentially composed with beta, and then we have alpha, which is the blue trace, running right up to the point Q. Note that the conclusion of the rule wants the result of the sequential composition to satisfy psi at all times between A and B. As such, the blue trace then from alpha needs to satisfy psi from time A all the way through time Q, at which point it terminates, and then the green trace from beta immediately begins. This green trace now needs to still satisfy psi from Q up until the point B, after which there are no requirements for the satisfaction of psi. For the phi part, the conclusion basically says that if alpha semicolon beta terminates, phi must be true. This is satisfied here in the example on the slide, since the green trace satisfies phi when it terminates. So that was case one. But what if alpha terminates after this time B? Remember, we need the sequential composition to satisfy psi from A all the way through B. Well, in that case, the blue trace from alpha needs to satisfy psi all the way from A through B, following which there are no requirements on that trace. And this part alone satisfies the box AB psi bit in the conclusion. And then for the phi part, we just need any beta, which again is the green trace in the figure on the right, to satisfy phi if it terminates, which is exactly what is happening here. Note that this box 0 B minus Q psi is vacuously satisfied since B minus Q is less than 0. And this is similar to how STL handles cases for box AB psi where B is less than A. So that was case 2. And then finally, for the third case, we might have alpha terminate before time A even begins. And in that case, there are really no satisfaction requirements on alpha, since Q is less than A, and as such, this box AQ psi becomes vacuously true. And then any following trace of beta, which is again the green trace, needs to satisfy psi at all times from A minus Q through B minus Q, and then also satisfy phi at the end if it terminates. And then all three of these cases, as I mentioned before, are encapsulated in the premise of the rule using this min-max notation. So far we have been talking about some background building up to STDL, following which we introduced STDL and then offered a glimpse into the proof calculus of STDL. I want to now quickly wrap up this talk with a brief discussion, following which I will be happy to answer any questions from the audience. First up, soundness and completeness in STDL. I had hinted before that our rules were sound, but I never formally stated this. Indeed, it is the case that the STDL proof calculus as a whole is sound. In other words, any derivable state formula in the calculus is actually a valid state formula. And then the STDL proof calculus is also complete relative to the first order logic of differential equations when this calculus is restricted to programs without non-deterministic finite repetition. Detailed proofs of these results are included in the paper for those in the audience who are interested. Indeed, we conjecture that the STDL proof calculus is fully complete, and this means including programs with repetition relative to the first order logic of differential equations, and then we leave a detailed proof of this conjecture as future work. Speaking of, as I've mentioned several times during this talk already, STDL is a big step forward in verifying crucial time-bounded safety and liveness properties in hybrid systems. Indeed, we have used this logic on several case studies from industry producing manual proofs, of course, to verify such properties, but there are still ways this logic can be improved. First, as hinted earlier, any properties proven by STDL involve manual proofs currently. So implementing the logic in a reasoning engine, say similar to Chimera X for a DL, is an important next step if the benefits of this logic are to be reaped for industrial use cases efficiently. Second, Adding support for a richer fragment of STL will likely be another major improvement to STDL. In particular, STDL does not support nested temporal operators for reasons that we highlight in the paper, and I'm happy to go over the reasons here if there is interest. For instance, STDL cannot reason about properties like box alpha, box AB, diamond CD phi, again, for some technical reasons that we highlight in the paper. And then finally, we would also like to formally prove the full completeness of STDL relative to the first order logic of differential equations, as I just hinted on the previous slide. To sum up then, I introduced to you STDL, a program logic that presents a fusion of STL and DL for the first time. The proof calculus for STDL is sound and complete relative to the first order logic of differential equations when this calculus is restricted to programs without non-deterministic repetition. And then finally, the first of its kind, the main takeaway here is that the first of its kind, STDL can verify crucial safety and liveness properties in given time intervals that are not handled by previous logics. With that said, thank you for viewing this talk, and I welcome any questions you might have, and I'd be happy to answer any of those questions or clarify any concepts that I may not have explained in detail. Thank you.